Chapter 2 homework quiz is due Sunday by midnight. I think it's 15 questions. Yeah, 15, and each question's worth 2 points. You have 2 tries on the homework quizzes, so if you get one wrong, try to take it again. I try to put feedback for most of the questions, so if you get it wrong, I try to give you hints or reasons that, common mistakes that a lot of people have made on those types of problems in the past to try to help you figure it out. And then the discussion, due every Sunday. So it's been, a lot of people have been forgetting the discussions. Every Sunday we have one due by midnight. And it's always on whatever topics we covered that week. This week is going to be velocities, accelerations, velocity problems, free fall problems, vector problems, which we'll talk about today as well. So there's a lot of topics to cover. Any questions you have, or any advice you have from someone else, some tricks that help you figure it out, works as well. You can even talk about the questions on the homework quizzes. So, all right, so on Monday, I think we covered 3 problems. So what we're doing now is we're basically just doing word problems. We have an equation sheet posted on Blackboard, and we're going to use this equation sheet to solve the word problems. Okay, so a good way to start word problems is always give a list of knowns and unknowns. Because if you notice from the equation sheet, there's a lot of equations possible. So if you have a list of knowns and unknowns, when you get to the step when you want to pick an equation, it's going to make it a lot easier. Okay, so let's start by looking at the problem itself and figuring out what our knowns are. What information did it give us? What's going to help us solve for what it's asking us to solve for? So in this example, what's happening is, this was a real world example actually. Colonel Stack, I believe was his name, conducted these experiments. He was trying to improve the harnesses on fighter jets. So up until this point, they didn't have ejection seats on fighter jets because they didn't think the person would survive if they did. So he did experiments to see what was the human limit for deceleration or for acceleration. How fast could a person slow down without dying, essentially? So when he did these experiments, he was actually the one in the seat when it reached the highest velocity, which is 283 meters per second. And I have a picture on the PowerPoints of that experiment. You can see his skin moving and everything is how fast he was slowing down. So he got up to 283 meters per second and then came to a stop in less than a second. So slowing down, a deceleration, very, very high deceleration. So when he did this, blood vessels in his eyes popped. He went temporarily blind. I mean, he had circulation issues, but he was alive. So it was great for the fact that now we can have those ejection seats, we have the harnesses, we improved fighter jets to give a fighting chance when needed. So what we're going to do is, using this velocity and the time to stop, we're going to calculate just how fast he decelerated. Okay, so the first piece of information given to us, and we're looking for numbers when I talk about information, is 283. So we need to figure out what that value is. So we have a set of variables. We have d for distance, v for velocity, a for acceleration, and then t for time. Those are the only variables we've talked about so far. So we need to figure out what variable that is. And what's going to help us with that is the units. So meters per second, that's actually a velocity. Just write these in steps. So it's going to be represented by the letter V. Okay, what else did they give us? Well, they said it took 0.624 seconds for him to stop. So seconds would be time. So that's going to be letter T. So we have the 2 knowns, the only 2 numbers given in that problem specifically. Then it says to calculate the deceleration. Well, deceleration is the same as acceleration. It's worded different because he's slowing down. So when we're speeding up, we say acceleration. When we're slowing down, we say deceleration. But they're both represented by the same variable. Both are going to be A. As we saw from Monday, when we calculated deceleration for one of those problems, the A value we got was negative. So when we solve for it, we should get a negative number since we're slowing down. So you get a positive number when you're speeding up, you get a negative number when you're slowing down. So now, the next step is to convert if necessary. What that means is you want to look at the units given to you and make sure they're in the units you want. So for instance, velocity is in meters per second. That's metric, that's good, that's what we want. If it was in miles per hour, we would have to convert it to meters per second. But since both of these are in the units we want, we have no conversions to do. So we get to skip that step. The next step would be to identify the type of problem and find an equation. So when I say identify the type, we've talked about two types so far. Zero initial velocity, so that's where the object was initially at rest, not moving, and then started to speed up. The other type is non-zero initial velocity. So this is where the object was moving at the beginning of the word problem and then slowed down. So let's see, what type is this? So it's saying that he was going 283 meters per second, and then the sled came to a stop. So he was initially moving. He was initially going 283, and then he slowed down. So this is going to be non-zero initial velocity. So why does this help me? Because it shows me on my equation sheet where to look. So if you look at your equation sheet, I got it separated into different types of equations. I have vector problems, which we haven't covered yet. And then I have zero initial velocity and non-zero. So now you know what column to look in for the appropriate equation. So the equations that we're looking at are going to be these guys, and I'm just going to write a few of them. So these are some possibilities of equations we're going to use to solve. Notice, since it's a non-zero initial velocity, all these equations have two velocities in them. They have a v sub I, which is initial velocity, and then a v, and this is going to be the final velocity. What did it end at? Okay, so I need to go back over to my variables and adjust. This velocity here, this 283, was that the velocity he was initially going, your vi, or was that the velocity at the end? So he was going 283, this is our initial. So what is the final? The final says he came to a stop. So if he was stopped, what was his velocity? You're not moving? Zero. Right? So we do have another piece of information here that wasn't explicitly given. We had to use the words to figure that one out. So that's the hard part on this one. So now that I have all the variables, all my knowns and unknowns, I take these and figure out what equation is going to work. Okay, so I need an equation that has vi, t, a, and v in it. So this first equation fits. So does the second equation. The third equation does not, because we don't have a d. Okay, so I know I'm not going to use this one. So I have these two to pick from. And what I want to do is I want to pick the one that's going to be easiest for me to use. And in this case, since a is what I'm solving for, I'm going to pick the one where a is equal to. Because that way I don't have to rearrange the equation. I can use the top equation, but I'm going to have to rearrange it to solve for a, and that could get messy. Whereas this one, I just simply plug in the numbers I have, solve. So, doing just that, we're going to take our final velocity, which was at a stop, so 0. We're going to subtract it, our initial velocity from that, and the initial velocity was 283. And then divide that by the time it took for him to stop. And that is 0.624. So, notice we're going to get a negative number, or a negative deceleration, because he's slowing down. So I said at the beginning that whenever you're slowing down, you should get a negative acceleration. When you're speeding up, you should get a positive. 453.5. Now the units on acceleration are meters per second squared. Units are very important. Okay, if you forget your units, or if you select an answer with the incorrect units, the whole answer is wrong. Okay, so make sure you're including them. This is especially important in lab because I know for all the lecture coursework, you're just picking a choice, so it makes it a little easier. But in lab, if you just write a number and don't put the units, that's still wrong because the number means nothing without the units. So make sure you know your units, make sure you're labeling. All right, so that is not our correct final answer because we learned about significant figures for a reason. We're still going to be using them. How do we use them? We look at the numbers given in the problem itself. So 283, we count how many sig figs in that number. There are 3. Time was also given to us. This first 0 doesn't count, so 3 again. So same, we want 3 in our answer. 1, 2, 3. Is that going to stay a 3 or go up? Go up to a 4. So I forgot my negative sign as well. Look at me. Don't forget your negative sign too. So negative 454 meters per second squared, indicating that they were slowing down. So that is an extremely high rate of deceleration. So what we're going to do now is we're going to use that acceleration and we're going to convert it to units of g. So I'm adding an extra layer onto this. So how many units of g? Okay, so what is units of g? Units of g is units of gravity. So this is actually a type of measurement or a type of representation that is used still today to figure out for rides, cars, other things, how many units of g that particular set has. So for example, if you like riding on roller coasters, you go to a roller coaster park, each ride actually has a classification of units of g. So I think 3 is about the highest they'll go, 3 units of g. That means that it's a very intense ride. You're slowing down. It's one of those where your stomach kind of goes up in your throat sort of thing. All right, so it's a way to measure the deceleration or acceleration of that particular ride. How fast is it slowing down? How fast is it speeding up? That way they can give you the limits and tell you if you've had neck injuries, don't go on this ride. Okay, so 3 is usually the max on rides. But let's see how many units of g this particular experiment had. So this is the human limit. This is the limit that humans can slow down without dying, essentially. Okay, so let's see what the limit is. So to figure out units of g, you can see on your equation sheet at the very bottom, the last sentence says units of g is equal to a over 9.8. So what that means is to calculate units of g, we want to take our acceleration, our a value, and divide it by 9.8. Why 9.8? Well, we're going to learn in the next chapter, the rate of gravity is 9.8 meters per second squared. So this units of g is gravity, and that's why we're dividing by 9.8. So to figure it out, we're going to take that 454 that we got for our a and divide it by 9.8. I just said most roller coasters are around 3. There might be a 5 here and there. And this is 46. I'm going to keep with our 3 sig figs. It's actually a unitless number because this is meters per second squared. Gravity is measured in meters per second squared as well. So there are no units on it. So this is the limit humans can handle. For fun, we do about 3 units of g on roller coasters. So big difference, right? All right. Questions on this one? So far? Okay. So what we're going to look at now is we're going to be using the same equations, but we're going to add a layer onto it. So we're going to talk about free fall problems. So free fall problems are problems in which an object is falling. Okay, whether it's an iron falling off an ironing board, or a person throwing a rock off a cliff, or a kid dropping their toy over a bridge. All of those would be free fall problems. Now free fall problems, we're going to use the non-zero initial velocity equations. Not the non-zero, sorry, the zero initial velocity. So zero initial velocity meaning if something falls, if my calculator were to fall off this table, well, it's a free fall problem because it's falling, but my calculator's initially at rest. Its initial velocity is zero. So that's why we're using the zero initial velocity equations for free fall, because the object's initially at rest before it starts falling. Okay? The key with these are our A, our acceleration, wherever you see A, is going to be equal to gravity. And I just said from the previous problem that gravity is 9.8 meters per second squared. So this is a tricky part of these problems because you're going to be trying to solve and look for an equation and you're going to be like, I don't have enough variables to solve. Well, because gravity is implied in the fact that it's a free fall problem. So let's look at an example so we can see what I mean by that. So say we have a cliff diver. And we're going to jump off, say, 27-meter cliff. We'll calculate how long that takes. Okay, so obviously when this diver jumps and he hits the water, by the time he hits the water, he's slowing down when it's zero. But we're talking about what is the peak velocity right before he hits the water. Okay, so it's free fall. How do I know it's free fall? Because they're jumping off a cliff. They're initially at rest until they step over. Once they step over, the only rate affecting them is the rate of gravity. So that's why we can put our A value set to gravity. So recognizing that this is a free fall problem gives us this extra piece of information. Because notice they don't tell us, your acceleration is 9.8. You have to figure that out by knowing, based off of the question itself, that it's a free fall problem. Because if I look at this, I approach it like my other problems. I write my knowns and my unknowns. Okay, well, I only see one number in this entire problem, and that's 27.0 meters. That's the height of the cliff. So when I write that as my known, that's going to be the variable d, distance. Distance, height, same thing. They're both measurements in meters. Well, I can't solve any of those equations with just one known variable. So I need to recognize that, wait, I don't have just one. It's a free fall problem. I also know what my A value is going to be, and that's going to be 9.8 meters per second squared. And I do have that written on your equation sheet as well. You can see at the bottom of those zero initial velocity and non-zero initial velocity problems, it says free fall, use zero initial velocity equations, and your A value is 9.8 meters per second squared. Okay, so there's reminders everywhere to help you figure that out. So, these are the knowns. What's my unknown? What is it asking me to solve for? Calculate time it takes, so time, and velocity reached, so v. So, two unknowns, that means we're going to need two different equations to solve. So we'll need more than one. Before we go to pick out our equations, we want to make sure our units are what we want them to be. So distances in meters, good. If it was in feet, kilometers, anything like that, we have to convert, but we don't. Acceleration, meters per second squared, that's good as well. So now I can find my equations. We just said we're looking at the zero initial velocity equations. So you know what columns to look in at least. So I'm going to skip the average ones and just look at these guys. right, so what equation is going to be useful? Let's see. Well, we're going to need more than one. Look at this first one. Velocity, do we have that? We do not. Acceleration, we have. Okay. Time, we don't have. So we can't use this one because we have two variables that we don't know. So we're going to keep looking. Now, this next one is the same situation. I know A, but I don't have B or T, so I can't use that one. At least not yet. So with this last one, do I have distance? Yes. 1/2 A, I have acceleration. So the only thing I don't have is time. So since I have just one unknown, this is the first equation I'm going to use. So you just kind of methodically go through and see what you have, what you don't have. So I'm going to use this equation, but notice I'm going to have to rearrange it. Now this is the hardest, or most people find this to be the hardest one to rearrange. So let's go step by step. Our goal to rearrange this equation is to get t by itself. I'm going to write it a little bit differently so it makes more sense here. So this 1/2, I just put the 1 up here and the 2 down there. Okay, it's going to make it easier to rearrange. So it's the same equation. So I just said I wanted the t all by itself. So that means I need to get rid of the a and the 2. I need to move them to this side of the equation. So how do I do that? Well, you perform the opposite operation. What that means is, for instance, here I'm dividing by 2. So if I want to get rid of 2, instead of dividing by it, I'm going to multiply by it. Whatever I do to one side of the equation, I have to do to the other. So I'm multiplying both sides by 2. What's going to happen over to the right here is now I have 2 in my numerator and a 2 in my denominator, right? Opposite sides of that horizontal line. So they're going to cancel. So I have effectively gotten rid of the 2 on that side of the equation. So now it looks like 2d is equal to at squared. Next step, let's get rid of my a. Well, I'm taking a and I'm multiplying it by t. So to get rid of it, I'm going to do the opposite of multiplication, which is division. So I'm going to divide by a. Whenever I have 2 of the same variable on opposite sides of that horizontal line, they cancel. Since I divided by a on the right side, I also need to do it on the other side. Whatever you do to one side of the equal sign, you have to do to the other. So now, getting closer, that's what my equation looks like right now. So I've moved all the variables over. My a's are almost like q's. But I don't have t quite by itself yet. It's t squared. I don't want it to be t squared. I want it to just be t. So how do you think you get rid of a squared? This is the tricky part. Square root, yes. I'm running out of space. That's how long this one takes to. So doing the square root, what that's going to do is it's going to get t by itself. So your equation is going to become, write it over here, t is now by itself is equal to the square root of 2d over a. So now we can take our d value, plug it in where d is, our acceleration, plug it in where a is, and solve. So time is going to equal 2 times 27 divided by 9.8. Don't forget to do this for 2 times 27 divided by 9.8. Obviously, I need to look at my sig figs. 2. Yes. Acceleration has 2. You just want 2. It's going to be 2.3. Units are going to be seconds. So it took that diver 2.3 seconds to reach the water. Right? Now that we have time, we'll be able to revisit our equations and solve for velocity. So when I'm solving for velocity, what I would do is pick the one where v is equal to. And what is that? Is it AT? Yeah. So v is equal to AT because I have my acceleration and now I have my time. So the acceleration is the rate of gravity because that's the only thing affecting him, right? He's going straight down into the water. So A times t, which we just said was 2.3 seconds. And we're going to get the velocity of 22.54, but we only want 2 sig figs. So I'm going to round that up to 23, and the units on velocity are meters per second. So he is going 23 meters per second when he hits the water. Now, I know that doesn't mean much because we don't think meters per second on a daily life. So for conversion practice, we're going to add on to this and we're going to convert our velocity to miles per hour so that we can envision just how fast he's going when he hits that water. Okay, so that's what I'm going to do over here. We're going to convert. We're going to take our 23 meters per second. So we're converting to miles per hour. And there is a conversion factor going directly there. It's the very first conversion factor on your chapter 2 equation sheet. So the conversion factor we're using is 0.447 meters per second is equal to 1 miles per hour. So it's just like those English to metric conversions. We do our little plus sign, our dimensional analysis. We take the original number we're trying to convert, and that's going to go here. Then we take our conversion factor we found and put it here. We just need to figure out which way it goes. So we want to cancel out meters per second, so we want the meter per second portion on the bottom, right? Opposite sides of that horizontal line, those units will cancel. We're no longer in meters per second. So that's going to put my 1 miles per hour on the top. So my units will be in miles per hour once I solve. So 23 divided by 0.447. Ooh, I would not want to be that diver. So I'm going to keep it at 2 sig figs. So I'm going to stop at 51. I don't need to round up. And this is miles per hour. So when that diver hit the water, he was going 51 miles per hour. That does not sound safe to me. Pretty fast. So think twice if you're going to jump off a 27-meter cliff. Well, hopefully think more than twice. But. All right, questions? Let's look at another free fall problem then. Next one, it needs a rock. Yes. Oh, 2 rocks of different masses. Well, it doesn't matter if there's 2, but we'll just say 1 rock for our purposes. So a rock dropped from a bridge. And these are all questions from the PowerPoint, so you can get the full versions. I'm just kind of cutting them down for the sake of writing time. Rock dropped from a bridge, hits water in 4.28 seconds. We're going to calculate height of the bridge and velocity of rocks right before they hit the water. Alright, so, knowns and unknowns. We'll start there, good place to start. Well, I only see one piece of information in the question itself. That's seconds. That's going to be my time. But I have another piece of information, and that is because I can recognize something was dropped from a high distance. So it's a free fall problem. So I also have my A. Gravity, 9.8. Not gravity, I swear. There. Okay, so what are my unknowns? What does it want me to solve for? Well, it says height, but that's not the letter H. That's the letter D, because height and distance are the same thing. Okay, and we also have our velocity that they want us to calculate. So how tall is the bridge? How fast are the rocks going? Never drop rocks off a bridge. Gravity speeds them up and they can do a lot of damage, right? So let's see, let's find our equations. Double check quick, we are in the units we want, so we're not doing the conversion step. So the equations, we are using the zero initial velocity equations, and we want to find one with these variables. So when I look at the distance equation, so if I wanted to solve for distance first, there's only two choices. The top one, d is equal to v average t. So that v average, that's average velocity. So I don't know average velocity, so that one won't work. So I go to my next d equation, and it's the one we just used and rearranged. This 1/2 at squared. And this one works for us because we have a and we have t. We don't even have to rearrange, we can just plug in our values. 4.28, we're going to square that. Can I get a distance of, how many sig figs did we want? 2? So I'm going to round this up. 90, and I'm putting a decimal after it so that that 0 matters, and I still have 2. So I got 89.7, so I rounded up to 90. And the units on distance, meters. So now I'm going to see how fast that rock is going once it went that full 90 meters. Okay, so to solve for velocity over here, velocity is just acceleration times time. So we're taking gravity multiplied by the time it took. How long did it get to fall? How long did gravity affect it? So 9.8 times 4.28. Once again, 2 sig figs, so I'm going to round that up to 42 meters per second. Going very fast. If we converted that into miles per hour, you would see it's at least 80 miles per hour, if not more. So, we do a lot of damage. All right. So, let's look at the last type of problem that we're going to see in this chapter, and that is vector problems. So we're looking at the only equations we haven't used yet. You'll notice these chapters are a lot shorter than chapter 1 was, because this is the end of the chapter right here. So I'm going to write the equations here. If you've taken trigonometry before, these are just rearrangements of triangle equations, so you might kind of recognize them. If not, don't worry, you just need to be able to use the equations presented to you. So, one thing about vector problems. Your calculator needs to be in degrees. So DEG, not radians, RAD. The most common mistake I have seen with these types of problems is people are calculating them and they're doing them correctly. I can see their work, but they're getting the wrong answer. Why? Because their calculator's in the wrong mode. So make sure it's in degrees and not radians. If you don't know how to do that, you can ask me, look it up, but get it in degrees. It's not going to affect any of the other problems that you do. It only affects problems when you're using the tangent, the sine, and the cosine functions. So what is a vector problem? I'll write an example of one, and then we'll apply it. We'll draw a picture of it to try to understand it better. So we're going to have somebody running. So a runner is going to jog 5.7 miles in a direction 65 degrees north of east. Calculate how far east and how far north. Okay. So vector problems are special for a few reasons. One of them being you're going to see degree sign. You're going to solve for degree sign. We're going to be talking about east and north. And also, whatever units, so for instance, this first piece of information is in miles. Usually when we see miles for all of the other problems that we do, we go, oh wait, I need to convert that. It needs to be in meters. Well, the nice thing about vector problems, you don't have to convert it. Whatever units it's in, keep it in those units. Your answer will just be in those units. So what I mean by that, this person that ran 5.7 miles, when we calculate how far east they went, the answer is going to be in miles. I don't have to convert to meters. Okay? So let's look at this with a picture. So we have an XY axis, just like graphing a map. It's back. All right, so the X direction. This is my east. And we're only going to look at this quadrant of an XY axis. We're not going to look at these other ones. So we're only going to see an east, and the Y is going to be the north. We're not going to look at south or west. Okay, we're just keeping this one little quadrant. So how I would depict this is this person is running 65 degrees north of east. What that means is, starting at the east axis, they're running 65 degrees, and this is a 90-degree angle. So they're running 65 degrees north of east. So I'm not bisecting that angle at 45. I'm doing it at approximately 65. This isn't to scale, but just trying to show how to figure that out. So this angle right here, this is my 65 degrees from the question. Okay? This is the vector that the person ran, the distance they ran. So this whole line right here is going to be my 5.7 miles. So what are they asking me to solve for? Okay? They want me to solve for the X and Y components, the east and north components. So they're saying this is where the person stopped. They started here at the origin, 0, 0. They ran 5.7 miles, 65 degrees north of east, and they stopped there. So what we're going to calculate is how far in the X direction did they go? So this distance here, and then how far in the Y direction did they go? This distance along the Y-axis, right? X being east, Y being north. Okay, so we are going to use these equations to figure those out. Well, we just talked about what X and Y were, right? X is the distance here, Y is the distance here. Well, what are A and theta? A is the vector itself, this guy here, at 5.7. Theta then is the only other piece of information we see, and theta is the degree sign. So whenever you see degrees, that's your theta, that's going to go there. When we're solving for these types of problems, you almost always have two unknowns that you have to solve for. So you're either going to be using these two equations to solve for X and Y, or using these two to solve for A and theta. So in this case, we're looking for X and Y, so we're going to use these top two equations. X is equal to A cosine theta, Y is equal to A sine theta. We just said our A is 5.7, our theta is 65. So we're just going to take those values and plug them in. So it's going to look like this. Our A is 5.7, And then we're going to press our cosine button on our calculator. Parentheses will pop up, and you'll enter 65 into those parentheses to get your x distance. Now it is a distance, so it's going to be in miles, just like the original a value was in. To solve for y, same thing, except for this time, instead of pressing the cosine button, you're pressing the sine button. So 5.7 cosine 65 gives me, and I want two sig figs when I'm looking at 2.4. So it's going to be 2.4 miles in the x direction. So how much in the y? 5.7 sine 65. If you are not getting the same answers as me, it's probably because your calculator is not in degrees. Okay? You're entering it the same way and getting the wrong answer because it's in radians instead of degrees. So you should be getting, rounding up, 5.2 miles for the y component. Almost on time. So, on Friday I'll post a few more of these vector problems since I only worked through one, just so you can see how to work them to solve for a and theta. But other than that, we have covered everything in the chapter with these first two videos. I'll just continue with a few more examples of this type of problem. So